Midnight strikes, and suddenly your production monitoring dashboard turns deep crimson. The connection count has hit its hard limit, and query latency is spiking into the tens of seconds. The immediate instinct of the team is to throw more hardware at the problem, doubling the RAM and CPU of the primary instance. But to everyone's horror, the performance does not improve. This is the PostgreSQL scaling illusion, the belief that vertical growth can solve architectural bottlenecks. PostgreSQL uses a process per connection model, meaning every new connection consumes significant memory and induces context switching overhead. Without understanding the underlying contention for locks and the overhead of the postmaster process, hardware upgrades are merely expensive bandages. This failure state is common in systems that ignore the fundamental limits of relational database engines. By the end of this lecture, you will master the 7-step decision matrix that prevents such catastrophic infrastructure failures and ensures your system scales predictably under any load. Scalability is not a single feature you turn on. It is a hierarchy of architectural decisions involving trade-offs between complexity and performance. Moving from simple query tuning to the sophisticated realms of distributed SQL requires a high degree of infrastructure competency. We must evaluate our system's maturity. Can we manage state across shards? Do we understand the latency implications of a global cluster? This lecture series will take you through a structured learning path. We begin with the low-hanging fruit of internal optimization and vertical expansion, then transition into the complexities of horizontal scaling using Citus and the modern distributed SQL paradigm. Each stage requires a different set of tools and a different mental model of how data flows through your system. It is about choosing the right tool for the right level of traffic while maintaining data integrity and system availability. But wait, before we jump into solutions, we must first learn how to accurately diagnose the specific type of pressure your database is under. In the world of PostgreSQL, bottlenecks are rarely monolithic. To solve them, we must categorize them into 4 primary domains: CPU, memory, I/O, and connections. CPU saturation often stems from poorly optimized joins or lack of functional indexes. Memory pressure targets the shared buffers and work mem, causing the engine to spill temporary data to slow disk storage. Connection exhaustion is particularly brutal because it starves the OS of resources, leading to too many clients' errors. Furthermore, we must distinguish between read-heavy workloads, which can be mitigated with caching and replicas, and write-heavy workloads, which are far more difficult to scale. A storage limit isn't just about disk space. It's about the IOPS throughput required for the write-ahead log to keep up with incoming transactions. Identifying which of these is your primary constraint determines whether you need a bigger machine or a completely different architecture. This approach might seem straightforward, but identifying the true root cause in a complex production environment is where most engineers fail. To navigate these bottlenecks effectively, I have developed a framework consisting of 7 distinct scaling methods. Each method represents a different level of architectural evolution. We start at phase 1 with indexing and query optimization. Phase 2 moves to vertical scaling. Phase 3 introduces connection pooling via tools like gridlock. Phase 4 utilizes read replicas for query offloading. Phase 5 leverages declarative partitioning for massive tables. Phase 6 is where we introduce Citus for sharding, and finally, Phase 7 covers the frontier of distributed SQL for global availability. This framework serves as your guide to determine when a simple index is enough and when it is time to re-architect your entire data layer. Choosing the wrong phase results in either wasted budget or a system that cannot survive the next traffic surge. Now that we have the roadmap, let's dive into the first critical step: why Phase 1, optimization and vertical expansion, is the foundation you absolutely cannot skip. In the world of database architecture, the most expensive way to solve a performance problem is by throwing more hardware at it immediately. Before we even consider scaling out, we must address the efficiency layer. Modern PostgreSQL optimization in 2026 isn't just about adding basic B-tree indexes. It's about strategic indexing like partial indexes, covering indexes using the include clause, and multi-column statistics. When a query performs a sequential scan on a table with millions of rows, it consumes massive I/O and CPU cycles that could be saved with a refined index. By utilizing explain analysis and identifying high-cost nodes in the execution plan, architects can often reduce resource consumption by 90% or more without spending a single cent on infrastructure upgrades. This is the foundation of the information management technologist's approach: software-level efficiency first. But what happens when the queries are fast, yet the system still feels sluggish under heavy load? One of the most common bottlenecks in PostgreSQL is its process per connection architecture. Every time a client connects, PostgreSQL forks a new backend process, which consumes roughly 10 MB of memory. In a high-traffic environment with thousands of application threads, this overhead leads to connection thrashing and severe context switching. This is why tools like PostgreSQL or the more modern, multi-core-aware PGCat are mandatory. These poolers sit between your application and the database, maintaining warm connections and multiplexing incoming requests. In 2026, we see more teams adopting transaction pooling over session pooling to drastically reduce the idle connection count. Without a robust pooling strategy, even the most powerful server will crumble under the weight of connection overhead long before the CPU hits 50%. But even with perfect pooling, we eventually hit a wall where the software can no longer compensate for the sheer volume of data. In the lifecycle of a database, you will eventually reach the efficiency wall. This is the saturation point where query tuning, indexing, and connection management yield diminishing returns. You might spend 20 hours of engineering time to gain a 1% performance improvement. From an IT strategy perspective, this is your signal to stop micro-optimizing and start expanding. When your IOPS are consistently maxed out and your cache-hit ratio drops, because the working set of data no longer fits in memory, your system is screaming for more resources. The mistake many make is trying to skip straight to complex sharding here. In reality, the most logical next step is often the simplest, vertical scaling. But how far can we push a single machine before the economics and physics of hardware stop us in our tracks? Vertical scaling, or scaling up, is the process of increasing the capacity of a single node by adding more CPU cores, RAM, and faster NVMe storage. In cloud environments like AWS or Azure, this is as simple as changing an instance type from an M6GX large to a M7GG.66 large. For PostgreSQL, the most critical resource is often RAM for the shared buffers and the operating system's file system cache. A larger memory footprint allows more of your database to reside in memory, reducing expensive disk I/O. As of 2026, enterprise-grade instances can support several terabytes of RAM, allowing even massive monolithic databases to run with incredible speed. This approach is highly favored for its simplicity. It requires zero changes to your application logic. However, this convenience comes with a steep price tag and a looming technical ceiling that every architect must prepare for. While scaling up is easy, it is not linear in terms of cost or performance. As you move into the extreme instance classes, the price-to-performance ratio begins to degrade. This is known as hardware diminishing returns. For example, doubling your CPU count might only yield a 60% increase in transaction throughput due to internal lock contention and memory bus limitations within the PostgreSQL engine itself. Furthermore, large NUMA, non-uniform memory access, architectures in high core count servers can introduce unexpected latencies if the database isn't tuned specifically for them. From a financial perspective, a single 128-core instance often costs significantly more than 432-core instances. This cost curve is the primary driver for moving toward horizontal strategies. If the machine gets too big, we aren't just paying more, we're also creating a massive liability. The most dangerous aspect of relying solely on vertical scaling is the single point of failure, or SPOF. No matter how powerful your server is, it still resides on a single piece of underlying hardware or a single availability zone. If that hardware fails, your entire system goes dark. Furthermore, maintenance becomes a nightmare. Scaling up usually requires a restart, leading to downtime that is unacceptable for 24/7 global services. As an information management technologist, you must evaluate the availability in the CIA triad. Relying on one giant box is a high-risk strategy that fails to provide high availability. This realization is what forces us into phase 2 of our scaling journey. We need to stop making the server bigger and start making it many. Are you ready to see how we distribute the read load across multiple replicas? In the next chapter, we dive into read replicas and the art of partitioning. When vertical expansion hits the inevitable ceiling of diminishing returns and escalating costs, we move toward horizontal read scaling. In a typical primary replica architecture, all write operations insert UPDAE directed to a single primary node. This node generates write-ahead logs, or WAL, which are then streamed to multiple read replicas. This strategy is highly effective for read-heavy workloads, such as dashboarding or content delivery, where the read-to-write ratio is often 10:1 or higher. By offloading complex select queries to these standby nodes, we preserve the primary node's CPU and memory for critical transaction processing. In modern 2026 cloud environments, the automation of these replica sets allows for rapid elasticity. However, this architecture introduces a fundamental shift from strong consistency to eventual consistency, which every architect must account for in the application logic. But what happens when the data on the replica isn't what the user just saved? This brings us to the most notorious challenge in horizontal scaling. Question: can your application handle the gap between a write and its visibility? The most significant hurdle in horizontal read scaling is replication lag. This is the time delay between a transaction being committed on the primary and it becoming visible on the replica. In high-traffic systems, network congestion or heavy query load on the replica can stretch this lag from milliseconds to several seconds. This creates the stale read problem. A user updates their profile, refreshes the page, but still sees the old data because the read was routed to a replica that hasn't caught up. From an engineering perspective, you must decide between asynchronous replication, which favors performance but risks data loss during failover, and synchronous replication, which guarantees zero data loss but significantly increases write latency. Many architects in 2026 utilize hot standby feedback or session-based routing to mitigate these issues, but the trade-off between availability and consistency remains a core architectural decision. Teaser yet, even with perfect replication, there is a hidden limit that no amount of read replicas can solve. Next, we identify the ultimate wall. We often see teams adding more and more read replicas to solve performance issues, only to find that the system still slows down. This is the write bottleneck. No matter how many read replicas you deploy, every single write must still go through the single primary node. In PostgreSQL, the primary node is the bottleneck for all DML operations and all WAL generation. If your workload becomes write-heavy, for instance, an IoT ingestion platform or a high-frequency trading system, you will eventually saturate the CPU and I/O of the largest possible single instance. At this point, the primary cannot process transactions fast enough to keep the replicas updated, causing replication lag to spiral out of control. This is the signal that horizontal read scaling has reached its utility limit. As a database architect, recognizing this write wall is crucial before the system experiences a total lockup. Before we jump into sharding to solve this, we should look at how we can optimize the internal structure of these massive tables to keep the primary breathing. When a single table grows into the multi-terabyte range, standard operations like indexing, vacuuming, and scanning become prohibitively expensive. This is where declarative partitioning, introduced in PostgreSQL 10 and significantly refined by 2026, becomes essential. Partitioning is the process of splitting one large logical table into multiple smaller physical pieces, called partitions. By using range list or hash partitioning, we can align data storage with how it's actually used, for example, storing orders by months. This architectural move drastically improves maintenance. Instead of vacuuming a 10 TB table, the engine only vacuums the active partitions. Furthermore, old data can be archived or dropped almost instantly by simply detaching a partition, avoiding the massive WAL generation and lock contention associated with a traditional delete command. Question, but how does this actually make a single query run faster? The performance magic of partitioning lies in a mechanism called partition pruning. When a query is executed with a filter on the partition key, the PostgreSQL query planner is smart enough to ignore all partitions that cannot possibly contain the requested data. For example, if you query for data from March 2026 on a table partitioned by month, the planner prunes the other 11 months before the execution even begins. This reduces disk I/O and memory usage by orders of magnitude because only a fraction of the total indexes and data blocks are loaded. In recent PostgreSQL versions, this pruning happens both at plan time and execution time, allowing for dynamic pruning even with nested queries or joins. This turns a sequential scan of a massive table into a targeted seek of a small partition. Teaser, however, partitioning is not a free lunch. It introduces strict constraints that can break your existing schema if you aren't careful. As an information management professional engineer, I must warn you, partitioning is an architectural commitment with significant trade-offs. The most common pitfall is the primary key constraint. In a partition table, any unique or primary key must include the partition key column, which might require a major schema redesign. Foreign keys referencing partition tables also have limitations, and global indexes that span all partitions do not exist in standard PostgreSQL. Furthermore, having too many partitions can actually degrade performance, as the planner spends more time analyzing metadata than executing the query. A common rule of thumb is to keep partitions in the hundreds, not thousands. You must weigh the benefits of pruning against the complexity of managing partition creation and the overhead of cross-partition queries. Bridge, when even partitioning and read replicas can't save your system from write volume death, we must move to the final frontier, sharding and distributed PostgreSQL. Let's look at phase 3. When your write volume exceeds the capacity of a single primary node and vertical scaling hits a financial or physical ceiling, you face the sharding threshold. Application-level sharding is often the first instinct. In this architecture, the backend application carries the burden of routing logic, deciding which database instance holds which specific row based on a shard key. While this avoids complex middleware, it creates a massive technical debt. You lose the ability to perform joins across shards, global constraints become impossible to enforce, and managing transactions across multiple database connections requires complex two-phase commit logic in your application code. This fragmentation often leads to siloed data where operational complexity grows exponentially with every new shard added to the cluster. Most teams find that the maintenance cost of keeping sharding logic in the application eventually outweighs the benefits. But what if we could move this complexity from the application layer back into the database engine itself? Question, is there a way to make a cluster of nodes behave like a single PostgreSQL instance? Enter Citus, an open-source PostgreSQL extension that transforms a single node into a distributed cluster. Unlike application-level sharding, Citus operates at the database layer using a coordinator and worker node architecture. When you send a query to the coordinator, it parses the SQL, identifies the relevance across the worker nodes, and parallelizes the execution. This allows you to scale out both your storage and your compute power horizontally while keeping the standard PostgreSQL interface. Tables are transparently partitioned into shards, which are just regular Postgres tables on the worker nodes. This means your application continues to use standard SQL, and Citus handles lifting of data distribution and query routing. It provides the scale-out benefits of NoSQL while retaining the ACID guarantees and relational power of PostgreSQL. However, this power comes with a critical requirement. You must design your schema for distribution. Payoff: the success of a Citus deployment depends entirely on how you choose to slice your data across these nodes. In a distributed Postgres environment, the shard key or distribution column is your most important architectural decision. If you pick the wrong key, you'll suffer from cross-node traffic, where the coordinator must constantly pull data from multiple workers to perform a single join, creating a massive network bottleneck. The goal is collocation, ensuring that related data, like a tenant's users and their respective orders, live on the same physical worker node. For SaaS applications, using tenant IDAS, the shard key is the gold standard because it allows 99% of queries to be executed locally on a single node. For high-volume IoT or event data, a device ID or user ID might be more appropriate. We must evaluate the trade-offs between distribution balance and query locality. A perfectly balanced cluster with high network latency for joins is often slower than a single large node. Teaser, but as we move into 2026, the industry is shifting away from managing extensions toward integrated cloud-native distributed engines. Let's see how they differ. Cloud-native PostgreSQL implementations like Amazon Aurora and Google Alloy DB represent a fundamental shift in how we think about scaling. They move away from the traditional shared nothing architecture of standard sharding and instead implement a log is the database philosophy. By decoupling the storage layer from the compute engine, these systems allow the storage to grow dynamically up to hundreds of terabytes without manual sharding. In Aurora, the storage layer is a purpose-built, log-structured distributed volume that replicates data 6 ways across 3 availability zones. This means the database engine doesn't have to wait for traditional checkpoints. It simply ships redo logs to the storage fleet. This architecture solves the IOPS bottleneck that plagues traditional Postgres on standard block storage. However, while these proprietary layers scale incredibly well, they lock you into a specific cloud provider's ecosystem. Question: is it possible to achieve this level of cloud-native scaling while staying truly open source and globally consistent? True distributed SQL engines like CockroachDB or YugabyteDB, which offer PostgreSQL compatibility, take scaling one step further by incorporating distributed consensus algorithms like Raft or Paxos. Unlike traditional primary replica setups where the primary is a single point of failure for writes, these systems treat all nodes as potential masters. Data is split into small units called ranges or tablets, which are replicated across the cluster. For any write to be confirmed, a majority of the replicas must agree, ensuring global consistency even in the face of network partitions. This is the ultimate solution for active-active multi-region deployments. You can serve users in London and New York simultaneously with low latency by keeping data close to them, while the database ensures that everyone sees a consistent state. It effectively solves the CAP theorem challenges by prioritizing consistency and partition tolerance. Payoff: this isn't just about more hardware, it's a fundamental rewrite of how data reaches consensus in a global network. Looking toward 2026, the landscape of PostgreSQL scaling is evolving into a global data fabric. We are moving away from managing individual database servers toward serverless, distributed Postgres. In this future, the boundary between a local database and a global cluster disappears. AI-driven auto-sharding will monitor query patterns in real time and move shards between regions to minimize latency before a human operator even notices a bottleneck. We will see standard Postgres increasingly adopting distributed features natively, blurring the lines between extensions like Citus and the core engine. As an architect, your role shifts from managing IOPS and vacuuming to designing high-level data topologies that span continents. You must prepare for a world where your database is no longer a single point on a map, but a living, breathing entity across the cloud. Bridge: now that we've explored everything from basic indexing to global distributed SQL, how do you decide which one to use? In the final chapter, I will give you the definitive decision tree for 2026. In the pursuit of infinite scalability, many architects fall into the trap of over-engineering. While Citus or distributed SQL offer impressive performance, they introduce significant operational complexity and hidden costs. For instance, managing a 100-node sharded cluster requires sophisticated monitoring, specialized backup orchestration, and a complete rethink of how global constraints like foreign keys are handled. In contrast, read replicas and connection pooling offer a high return on investment with minimal architectural friction. A true information management professional engineer doesn't just look at throughput. They weigh the total cost of ownership, including developer productivity and system reliability. Choosing a scaling path that exceeds your operational maturity is a recipe for catastrophic downtime. But where exactly does the threshold lie? Let's visualize the transition points where the cost of staying on a single node outweighs the pain of moving to a distributed architecture. The scaling ladder serves as a strategic roadmap for database evolution. You should never skip levels. It begins with internal optimization, where we tune the engine, refine indexes, and implement connection pooling to maximize the current hardware. When CPU or memory reaches its 70% threshold consistently, we move to phase 2 offloading, introducing read replicas to separate traffic. Only when the primary node's write capacity is exhausted do we consider phase 3, structural partitioning. Finally, for hypergrowth scenarios exceeding tens of terabytes or hundreds of thousands of write requests per second, we trigger Phase 4, distribution using Citus or distributed SQL. This phased approach ensures that every architectural shift is justified by business demand rather than technical curiosity. But how do we decide which level is appropriate for our current state? This requires a set of professional principles to avoid the pitfalls of premature optimization. From the perspective of a seasoned database architect, the greatest risk to a system is not lack of scale, but excessive complexity. We often see teams implement Citus for datasets that could easily fit into the memory of a single high-performance instance. Remember, complexity is the enemy of reliability. In 2026, with the rise of NVMe storage and high core count processors, a single PostgreSQL node can handle far more than it could a decade ago. Your primary goal should be to keep the architecture as simple as possible for as long as possible. When you do eventually shard, do it because the telemetry leaves you no other choice. A professional engineer builds systems that are maintainable by the average developer on the team, not just the architect who designed it. Now that we understand the philosophical foundation, let's synthesize everything we've learned into a master reference guide for your next production deployment. Throughout this lecture, we have explored 7 distinct methods to scale PostgreSQL. We started with vertical scaling and connection pooling as the foundation. We then moved to indexing and partitioning to manage data access patterns. Finally, we scaled out using read replicas, Citus sharding, and distributed SQL. Each of these tools has a specific sweet spot. For example, partitioning is excellent for lifecycle management, but does not solve write-lock tension. Citus provides massive write scale, but requires a careful key selection to prevent cross-node traffic. Distributed SQL offers the highest resilience, but at the cost of network latency. To succeed in 2026, you must become an orchestrator who knows exactly when to pull each lever. But how healthy is your current database right now? Let's go through a diagnostic checklist to evaluate your system's readiness for the next level of traffic. To determine your next move, you need to conduct a health check across 4 dimensions: connection pressure, I/O saturation, locking contention, and data volume. If your active connections frequently hit the max connections limit, you need a pooler, not more hardware. If your vacuum processes cannot keep up with the dead tuple rate, you need partitioning to reduce the scan surface. If your write latency spikes during peak hours despite fast storage, it's time to look at sharding. Use this checklist as your diagnostic guide. If more than 3 items are marked as warning, your current architecture is likely to break within the next 6 months. Addressing these issues proactively is what separates a reactive developer from a strategic architect. But what about the common myths that lead people astray? Let's clear those up in our final rapid-fire FAQ session. As we conclude, let's address the misconceptions that often derail scaling projects. Many believe that distributed SQL is a magic bullet for all Postgres problems. It is not. The network is still the bottleneck for distributed transactions. Others think sharding means you lose ACD. With modern extensions like Citus, this is no longer true, provided you understand the scope of your transactions. The most important lesson for 2026 is that the database is no longer a static box. It is a living, evolving organism. By mastering these 7 methods, you have equipped yourself to handle any traffic surge, from the 1,000 users to the first 100 million. Your journey doesn't end here. The landscape of data is shifting toward AI-integrated vector databases and serverless architectures. This concludes our masterclass on PostgreSQL scaling. Keep building, keep measuring, and never let your architecture be the reason your system breaks.